program, we're going to go over DC motors, the different types available, how they operate, and the methods used to start them.
We'll also look at the different circuits used to accelerate and decelerate to control the speed of the motor. At the end of the module, we'll conclude with the troubleshooting of the different kinds of DC motors. So, let's start by looking at the basic operation of a DC motor.
DC motors are generally found in applications requiring adjustable speed and simple torque control. Such applications include cranes, elevators, printing presses, and many others. DC motors are composed of three basic assemblies, which are the motor frame, the armature, and the end plates or brackets. The armature consists of rotating windings, while the frame holds stationary windings. The end plates hold both sides of the motor. There are three basic types of DC motors, namely a series DC motor, a shunt DC motor, and a DC compound motor. The series DC motor is characterized as a provider of high starting torque and is able to move large shaft loads when it is first energized. In this motor, the series field windings, which are composed of heavy gauge wire, are connected in series with the armature winding. The wires coming from the series field are labeled S1 and S2, and the armatures are labeled A1 and A2. The electrical representation of this motor is given by this circuit, where the series field is also shown in series with the armature. The shunt DC motor has its field winding, which is made up of many turns of small gauge wire, connected in parallel to the armature. This motor has a very low starting torque, which requires a small shaft load. At full speed, this motor will remain rather constant. Note that the terminals coming from the shunt field are labeled F1 and F2. The armature and field can be controlled by two different power sources, in which case the motor can be speed controlled by changing the field current. This circuit represents a typical shunt DC motor with the same power source. The DC compound motor is a combination of a series motor and a shunt motor. It has a series field winding which is connected in series with the armature and a shunt field connected in parallel with the armature. This configuration allows the compound motor to provide high starting torque and good speed regulation. The circuit representation of this motor is shown by this diagram.
We know that the main stationary electrical component of a DC motor is the frame to which the main field assembly is attached. This field assembly is composed of the so-called poles, which are formed of stamped laminations securely bolted to the frame. These field poles are wound with wire to form the field coils. These coils are the ones that form the fields represented in the series DC motor, the shunt DC motor, and in the compound DC motor. As can be seen in these diagrams, the field windings are shown stationary. The field poles attached to the frame are accompanied by interpoles which are positioned between the field poles and are made up of a pole piece and a coil. These interpoles form an essential part of the field by providing reduction or elimination of sparking due to induced voltages created by the armature current flowing through the armature coils. The main rotating component of the DC motor is the armature, which holds the shaft of the motor and a cooling fan. The armature coil is formed by laminated slots which have been wound through the slots. The ends of the coils in the armature are connected to what's known as the commutator. The commutator is made up of many separate bars or segments which are separated by insulators. Each of these bars are connected to the armature coils. A commutator is perhaps the most critical single part of a DC motor. Its design and manufacture must ensure a perfectly round, concentric, and heat-stable surface for the brushes to ride on. The brushes are small blocks of special carbon that function as the interface between the external power source and the commutator. These brushes are mounted in brush holders made of brass with a stainless steel brush finger under spring tension. This spring is designed to give constant pressure throughout the life of a brush, regardless of wear. The brush must be properly seated in the holder and pressed firmly against the commutator. This brush holder must have a clearance of about 1/16 of an inch between the commutator surface touching the brush. Too much space, due to an inclination of the holder, will cause the brush tip to break. If it is too close, it will also cause it to chatter and burn. If the brush becomes broken, there will not be a good contact between the commutator and the brush, and it will show up as an open circuit condition. A motor will have an even number of brushes, half of them connected to a positive terminal and the other half to the negative. In general, the number of brushes in a motor equals the number of field poles. These brushes wear out with use and need to be replaced once they reach a certain wear mark which is located on the brush. When a new set of brushes is installed, it is important that the brushes be properly seated to fit on the commutator. The brush's wear should be checked periodically during the preventive maintenance. The brush assembly is mounted on the rear end plate for easy reach, where an access hole or opening is provided for motor inspection and for adjustment of the brushes and holders. The on-off state of DC motors can be controlled using one-pole or two-pole manual or magnetic starters. As we know, the manual starter is activated by an on-off or start-stop switch, whereas the magnetic starter turns the motor on and off by closing or opening the starter contacts. In a DC motor control, it is only necessary to switch or break one side of the line power, usually the positive. The magnetic starter, as we know, turns on and off the motor by closing or opening the contacts. This is generally represented in the standard start-stop ladder diagram or in the wiring diagram. There are two basic methods used for starting DC motors, which are full voltage starting and reduced voltage starting. Full voltage starting is confined to DC motors rated 2 horsepower or less, while reduced voltage starting is used for the larger motors. Full voltage starting, also called across the line, consists of applying full voltage to the motor. This can be accomplished with manually operated switches, manual starters, or magnetic starters for either 2-wire or 3-wire control circuits.
The main reason DC motors above 2 horsepower are reduced started is because DC motors draw very high currents due to the very low resistance of the armature windings. This low resistance design is implemented to minimize heat losses. If these 2 horsepower or larger DC motors are started with a full line voltage, heavy current flowing through the winding while at rest might cause permanent damage to the motor.
The simplest form of reduced speed in a DC motor is accomplished by placing a variable resistor or rheostat in series with the armature winding or the field winding. These rheostats are available in a 3-point or 4-point starting box, so named because of the number of terminals used. The application of a 3-point rheostat reduced voltage start is fairly basic. For example, in this compound DC motor circuit, as the moving handle is rotated following the resistance arc, voltage is applied to the motor circuit, thus accelerating the speed of rotation. Note that the resistance is being varied, therefore implementing a reduced voltage start. It starts at a low speed and gradually increases to full speed as the resistance is reduced. When the handle is moved all the way, a coil will hold the handle. In the event that the circuit interrupted, the holding coil de-energizes and the handle is spring returned to its original off position. This allows for low voltage protection. Reversing DC motors requires reversal of current flow through either the armature or the field, but not both. If both were reversed, the net result would be rotation in the original direction. The de facto standard in industry is usually to reverse the current through the armature. Note that in DC, the current flows from negative to positive. The most common method for reversing DC motors is using manual starters, magnetic starters, or drum switches. The drum switch can be used to reverse the series DC motor, the shunt DC motor, or the compound DC motor. The only thing that will vary is the terminal connection wiring. Let's take the series DC motor. As we can see, in the forward position, the current will flow from the negative to the positive through the armature and the field winding. Once the drum is switched to reverse, the current that flows through the brushes and commutator will be reversed, thus reversing the rotation of the motor. During the forward cycle of the motor, the current through the armature goes from here to here, and during the reverse cycle, it goes the opposite way, from here to here.
Reversing DC motors with either manual or magnetic starters follows the same principle, which is the reversing of current flow through the armature. The contact arrangement and interlocking is basically the same for both starters. Let's take a magnetic starter and create the circuit for reversing the rotation of a series DC motor.
We know that we can control a DC motor by breaking only one of the power lines, therefore requiring only one set of contacts. However, due to the number of connections that need to take place for reversing, we'll need 3 sets of contacts for each, the forward and the reverse starters. We only need, though, one set of overload relays. For the forward direction, we would connect this wiring diagram like this, where the field is in series with the armature and the positive is connected to one side. In this case, to the field, while the negative goes to the other side of the armature. The remaining contact is used to connect the A2 side of the armature to the S1 side of the field winding series. To reverse the motor, we need to reverse the positive and negative power lines to the armature. To implement this, we would use the contacts of the reversing starter to redirect the wiring. The side A2 of the armature that used to be positive will now be switched to the negative, while the other one will be in series with the field, connected through the contacts to the S1 side of the winding. The positive terminal goes to the S2 side of the field. Note that the overload protection is available for both the forward and reverse conditions. This magnetic starter configuration may be controlled by a circuit like this, where mechanical interlock prevents it from being reversed while in the forward motion and vice versa. Or it may have additional normally closed contacts from the forward and reverse coils to interlock the 2 circuits and make them mutually exclusive. This is a compelling circuit because the operator is compelled to stop it before changing the direction of the motor. Reversing the shunt DC motor and compound DC motor is also very similar, and as we'll see, the main thing to remember is to reverse only the direction of either the field or the armature. In the case of the compounds, you'd have to change the direction of both the shunt and the series fields. For this shunt DC motor circuit, we would connect the forward direction like this, where the positive and negative terminals are in parallel with the shunt field and the armature. Note that the shunt field connection to F1 is straight from the negative side because it does not need to be switched. The reverse connection would be like this, where the positive and negative terminals are switched to A2 and A1. In the reversal circuit, note that the positive is still going to the same terminal, F2, in the shunt field. The connections for a compound DC motor in the forward direction follow the same design. The reversal starter switches the negative terminal from A1 to A2, and the series connection to the field from S1 to A1.
As we know, DC motors are used in industrial applications, requiring most of the time variable speed control and high torque. In fact, DC motors can be controlled from rest or 0 speed to full speed. DC motors provide 4 to 5 times its rated torque for a short period of time, whereas the AC motor would stall most of the time if its load requires even twice the rated torque.
The speed of a DC motor can be changed by using a variable source of voltage to the armature, where an efficient and smooth control of speed can be achieved for either reversing or non-reversing duty. Control of the voltage of the series or shunt fields can also be combined with the armature speed control. Of all DC motors, the series DC motor offers the poorest speed regulation, but the highest starting torque. As can be seen in the graph, the series motor is suitable for low-speed applications which require high torque by heavy loads. In this motor, the speed changes as the torque changes. When the torque is high, the speed is low. As the load is removed, the torque is reduced and the speed will rapidly increase. This is why a series DC motor without a load could gain enough speed and be in a runaway condition and incur serious damage. Therefore, the series motor should always be connected directly to the load and not through belts, chains, or any other mechanisms. The speed of the series motor can be controlled by varying the applied voltage. This series motor speed control is considered relatively poor when compared to the control achieved in a shunt motor. Its greatest advantage, however, is the tremendous high starting torque it provides.
The starter motor in your car is a typical example of a series DC motor, where speed regulation is not as important as the required starting high torque to crank up the car.
The shunt DC motor, in contrast, provides good speed-torque characteristics. The speed in the shunt motor can be regulated by the applied armature voltage or by the applied field voltage. If the voltage applied to the armature is reduced, the speed of the motor will also be reduced. If the field voltage is reduced while the armature is maintained constant, the speed of the motor will increase. This increase in speed is due to the reduction of field strength, which reduces the counter-electromotive force which is developed in the armature, thus allowing the armature to go at a faster speed. Once the field voltage is set, it remains fairly constant, even if the armature current is changed, thus providing a constant speed. If the load increases, the current through the armature will increase, and so will the torque. The speed, however, once set by the field voltage, will tend to keep the motor at the set speed. The compound DC motor combines the characteristics of the series and shunt motors. It provides a compromise in performance between the other two DC motors by offering good starting torque and relatively good speed stability. The starting torque and speed regulation are not as good if compared to the series and shunt motors, respectively. The speed of the compound motor can be obtained by regulating the applied voltage to the field or to the armature in a similar manner as the series and shunt motors.
In Part 2 of this program, we'll cover different methods and circuits used to accelerate and decelerate DC motors. We'll also present an introduction on how a DC drive regulates the speed of a DC motor, and conclude with how we go about troubleshooting the different types of DC motors.